So this is joint work with Hans and Nicola at Charles University and with Barney and Daniel at Durham. And we look at the complexity of acyclic colouring, star colouring and injective colouring for H3 graphs. So we start with some definition. An acyclic K-colouring of a graph is a proper K-colouring such that the graph induced by the vertices of any two colour classes is a forest. So in other words, any cycle gets at least three colours. And so here we have C4. Obviously it can be coloured with two colours, but in an acyclic colouring we need at least three. And on to star colouring. So star K-colouring of a graph G is a proper K-colouring such that the union of any two colour classes induces a star forest. So in other words, any cycle and any path on at least four vertices is assigned at least three different colours. And if we look at C5, this can be coloured and acyclic coloured with three colours, but in a star colouring we need at least four, because when we use only three colours we must get some bichromatic P4. An injective K-colouring. So an injective K-colouring of graph G is a proper K-colouring such that the union of any two colour classes induces a disjoint union of edges and vertices. So in other words, any path on three vertices is assigned three different colours. And so here we have the claw K13, and what we notice is that it requires two colours in any colouring and any acyclic colouring, also in any star colouring, but we need four different colours in injective colouring. And one thing to note is that injective colouring is polynomial times solvable for fixed K equals 3, because these graphs must have maximum degree 2 in order to be injective 3 colourable. And another thing to note is that sometimes injective colouring is defined such that the colouring doesn't have to be proper, so it's just that the neighbourhood of any vertex, in the neighbourhood of any vertex, each vertex must have a different colour, but we do require the colouring to be proper. And in this case, the problem is the same as distance 2 colouring or L11 labelling. And this gives rise to two decision problems for each of our three colouring variants. So for fixed K, we're given a graph G and we ask, does it have an acyclic or star or an injective colouring with at most K colours? And when K is part of the input, so we give a graph G and an integer K as part of the input, and does there exist an acyclic or a star or an injective colouring with at most K colours? H3 graphs. A graph is said to be H3 for some H if it has no induced subgraph isomorphic to H. So this diamond has a triangle as an induced subgraph in the blue vertices, but although it has C4 as a subgraph, it doesn't have C4 as an induced subgraph, so it's C4 free. And what do we know about colouring for H3 graphs? So there's been a lot of study into this, and actually we have a complete dichotomy when K is part of the input. So colouring is polynomial time solvable for H3 graphs if H is an induced subgraph of P4 or P3 plus P1, and NP complete otherwise. And when K is fixed, colouring is known to be NP complete for H3 graphs when H contains a claw or a cycle. And this leaves us with the case of where H is a forest of maximum degree 2, and it's called a linear forest. And there are a lot of results in these cases, but there are infinitely many open cases. So for example, 3 colouring is open for PT3 graphs with T at least 8, and K colouring is open for SP4 free graphs with K at least 3, S at least 2. Our results. So first, we show that each of the 3 problems is NP complete when H contains a claw or a cycle and K is fixed. And we do this in a similar way to the way that this is shown for colouring. And then we study the remaining open cases to obtain complete dichotomies when K is fixed and almost complete classifications when K is part of the input. So for acyclic colouring, as we said, we have this complete dichotomy when K is fixed, so the problem is NP complete when H contains a chlorocycle and polynomial time solvable otherwise. And then we also have some results for linear forests, but a finite number of open cases when K is part of the input. And similarly for star colouring, so we fully classify every case except H is 2p2. So again, we have this complete classification when K is fixed, and when K is part of the input, it's polynomial time solvable if H is an induced subgraph of P4, and NP complete otherwise when H isn't 2p2. And finally, injective colouring, so again, a complete classification when K is fixed. We have results for most linear forests when K is part of the input, but we're still left with a finite number of open cases. So first we'll look at the case of chlor-free graphs. So for acyclic colouring, what we do is we extend this result of Allen and Sachs, which shows that acyclic 3-edge colouring is NP complete, to show that acyclic K-edge colouring is NP complete for K at least 4. And what this then shows is that acyclic K colouring is NP complete for line graphs, and since line graphs are chlor-free, this gives us NP completeness for chlor-free graphs. And then a similar case for star colouring. So we extend this result that star 3-edge colouring is NP complete to show that star K-edge colouring is NP complete. And then we use this observation that a graph has a star K-edge colouring if and only if its line graph has a star K colouring to show NP completeness for line graphs and hence for chlor-free graphs. And then finally injective colouring, so this was a known result that strong K-edge colouring is NP complete for bipartite graphs of girth at least G. And what we notice is that strong K-edge colouring is the same problem as injective K-edge colouring. So again, we get NP completeness for line graphs and hence for chlor-free graphs. And now the case where H contains a cycle. So for acyclic colouring, we actually have an NP completeness result for graphs of arbitrary girth. And the way that we prove this is similar to the proof that K colouring is NP complete for the 3 colouring is NP complete for graphs of arbitrary girth. So what we do is we start with a graph which is 4 chromatic, and then we delete edges until we get a graph which is acyclic 3 colorable. And we call this graph f dash, where f dash plus xy is not acyclic 3 colorable because xy is the last edge removed. And then from this we create a gadget to replace the edges of the graph in a reduction from acyclic 3 color. And how do we do this? Well, we have several possibilities based on the properties of f dash, but the most straightforward one is the case where every acyclic coloring of f dash gives the vertices x and y, so the vertices the last edge removed, different colours. And in this case, what we do is we take an edge uv in our graph G, and we identify u with x and v with y in a copy of f dash to get our new graph G dash. And when we show that G dash is acyclically 3 colorable if and only if G is. And why is that? Well, clearly if G is acyclically 3 colorable, we can extend this to an acyclic 3 coloring of G dash using any acyclic 3 coloring of F dash. And in the other direction, what we have to note is that since F dash plus the edge xy is not acyclic 3 colorable, it must be that however we color x and y, we have a path in these two colors between the two vertices in f dash. But then, since G dash is acyclic 3 coloring, we don't have this path in G. So therefore, when we add the edge uv back, we get an acyclic 3 coloring of G. So by adding a dominating vertex in this construction, we get NP completeness to the cyclic k-coloring for H3 graphs where H contains a cycle with length at least 4. And then we use the theorem of common and chi to cover the triangle-free case for k at least 4. And putting this all together, we get that for any k at least 3, a cyclic k-coloring is NP complete for H3 graphs where H contains a cycle. Star coloring, so we first show the star k-coloring is NP complete for H3 graphs where H contains a cycle of length at least 4, and what we do is we reduce from 3 coloring for graphs of girth at least p plus 1 where p is the length of our cycle by replacing each edge with the gadgets shown below, and then what we get is our new graph has no cycles of length less than p plus 1 except for triangles. So, in other words, it's CP3. And then we combine this with the result of Albertson to show that, which says that for any k at least 3, star k coloring is NP complete for bipartite graphs. So this gives us the triangle-free case. So together we get star k coloring is NP complete for H3 graphs where H contains a cycle for any k at least 3. And finally, injective coloring. So first we show that for k at least 4, injective k coloring is NP complete for bipartite graphs. And then we combine this with the result that we saw earlier, which tells us that star k coloring is NP complete for H3 graphs where H is the cycle of length at least 4. So now we've covered the case of claws and cycles, we're on to the case where H is a linear forest. So first we have a general polynomial result when k is fixed. So the first thing to note is that if we take a balanced bicyclic of size k, then it's not acyclic or star k colorable, since no color appears in both parts, but if in both parts there is a color that appears at least twice, we'll get a bichromatic C4. So a balanced bicyclic of size k needs at least k plus 1 colors. And similarly for injective coloring, it's even easier, so a balanced bicyclic of size k, since it has diameter 2, needs 2k colors. But knowing that if my graph has a balanced bicyclic of size k, it's not going to be k acyclic star or injective colorable, we can use this result of Laslaw's and Reskin to show that each of the problems are polynomial time solvable for H3 graphs where H contains a linear forest. So for any pair of integers L and K, there exists a constant B of LK such that every graph of tree width, at least B, contains an induced path of length L or a balanced bicyclic of size K. And we know that our graph is PL3, so either it has true width at most this constant value, in which case we can solve each of the problems in polynomial time, or it's not K star acyclic or injective colorable. So each of the problems can be solved in polynomial time if H is a linear forest. So now the case where K is part of the input. So first we have this result of lines, which says that acyclic and star coloring are polynomial time solvable when H is an induced subgraph of P4. And then we have this theorem, which shows that cyclic coloring is NP complete for 19P1, 3P3, 2P5 free graphs. And this is quite a complicated construction, which I won't go over now, but it does leave us with only finitely many open cases for acyclic coloring. And star coloring, well, first we show that star coloring is NP complete for co-bipartite graphs. So what we notice is that a star coloring of a co-bipartite graph is equivalent to a clique covering of its complement, which is a bipartite graph. And in this clique covering, no two clique classes can induce either the complement of P4, which is P4, or the complement of a cycle. So in particular, the complement of C4 is 2P2. And then, since the complement is bipartite, the vertices of any two clique classes of size at least 2 induce a biclique. And since any clique class in a clique covering of a triangle-free graph has size at most 2, we just need to maximize the number of clique classes of size 2. So my graph can be star-colored with K colors, if and only if its complement contains a balanced biclique with n minus k plus 1 vertices. And this problem of finding a maximum size balanced biclique in a bipartite graph is known to be NP-complete. So star coloring is NP-complete for co-bipartite graphs, so in particular the 3p1 free graphs. So combining this with the result from lines that we saw earlier, we know that star coloring is polynomial time solvable for H true graphs where H is an induced subgraph of P4, and NP-complete where H is any other linear forest except for 2P2. So this is our only open case for star coloring. And then injective coloring, so this is polynomial time solvable for H true graphs where H is an induced subgraph of P4, or P3 plus P1. So for the P4 free case, we just note that a P4 free graph has diameter 2, and since injective coloring is equivalent to distance 2 coloring, this means that no two vertices can be colored alike. So we need n colors in any injective coloring. And for H induced subgraph of P3 plus P1, we use the result of Larry for porphyry graphs, which states that each connected component of the complement of G is either triangle-free or complete multipartite. So then we note again that an injective coloring of G corresponds to a clique covering of its complement, such that each edge within a clique class dominates the complement. So no two clique classes induce the complement of P3, which is 2P2 plus P1. So unless the complement is connected, no edge dominates. So if the complement is disconnected, no two vertices get the same color. But otherwise, the complement is either triangle-free or complete multipartite. So if it's triangle-free, the maximum size of the clique class is 2, and we're just looking for a maximum matching among dominating edges. Otherwise, if it's complete multipartite, well, every edge in a complete multipartite graph must dominate. So the minimum size of a clique covering is the maximum size of a part in the partition. And then we have this result, injective coloring is NP-complete for split graphs, so for 2P2 free graphs. And combining this with what we know so far, we're left with linear forests where one component is a path of length at most 4, and the rest are isolated vertices. And finally we have this result, injective coloring is NP-complete for 6P1 free graphs. And we show this by reducing from the coloring problem, given a partition of a graph into 4 cliques. And what we do is we have the fifth clique with one vertex for each edge in my original graph, and I then replace each edge by 2 edges, one from each of its endpoints for the corresponding vertex in my new clique, to get a graph which has an injective coloring of K colors if and only if G has a coloring with K colors. So on to open problems. Well, for acyclic coloring, we have these 1,991 open linear forests, and the smallest case is 4P1 and 2b2. And we think now that we can prove acyclic K-coloring is NP complete for graphs of girth at least G for any K at least 3, as opposed to just for K equals 3 as we showed here. And then star coloring, so we have one open case of star coloring for 2b2 free graphs. And then we proved we think that star 3 coloring is NP complete for graphs of girth at least G for any G at least 3. And we would like to